Okay, thank you very much for inviting me. I'm Francesco Zappa from Imbria, and this is based on some work that I've done with some great colleagues like Robin Morissette, Pankaj Pawan, Victor Vafeyadis, Thibaut Golabonsky, and Shoam Chakraborty. So, where do I want to start? I'd like to start from some code. Okay, so please, let's check this. Imagine that we have some shared memory. Okay, two variables, A and B. A is initialized with 1 and B with 0. Okay, and then we have two threads sharing the memory. And thread 2 does B equal 42, why not? And then print B. That's easy. What about thread 1? Well, it starts with a loop 4 times, and then it says, if A is 1, then return. And indeed A is 1. And thread 1 will return without executing this line, and in practice without modifying B at all. So we can deduce that thread 2 is not affected by thread 1, and vice versa. And now, your mileage may vary, but I do expect this program to print 42. Now, we compile it with GCC 407 at -02, and sometimes we get 0. So what we can do is start looking at what GCC generated. Okay, this is the assembly. Okay, and the first remark is that the outer loop, so the 4S, can be, and actually it is, optimized away. And then the assembly code generated is, well, it loads A into register A, it loads B into register B, it loads B into register B. Bit odd, but why not? And then it says if A is 1, then jump to L2. And at L2, what do we find? The generated assembly restores the old value of B into the memory B, and then returns 0. Now, what can we deduce? Well, the compile code saves and restores B. This is perfect. This is a bit odd, but it is perfectly fine in a sequential setting. You can run your program, and you will not observe this memory operation on B. But if we put this code in a concurrent setting, then what do we have? Well, then, well, we can read 1 into register A, then we read 0 into register B, and then we update B with 42, and then we restore B, we restore 0 into B, and in turn we print 0 instead of 42. Now, this was my reaction. And actually, my reaction was, come on, C can't be so nasty. This must be a subtle miscompilation. But maybe those back in the end of the audience disagree with me and might say, of course he allows this. Why do we bother? So the question is, what is C? Well, C is lots of things. It can be Kernighan-Ricci, it can be NCC, it can be the C99, it can be C11, so all the standards by this committee. And there is something which I would call the de facto C, which is whatever C compilers implement and whatever C programmers rely on. And it is not guaranteed that all these are in sync. So, a bit of history. When it comes to concurrency, so since the 80s, there was widespread use of threads in the C language, but there was no specification, and there was definitely a poor understanding of the constraints of using thread on a shared memory environment. And from 2005 onwards, there was a proposal by Hans Böhm and Sarita Adve, and then there was, which led to the C++ OX concurrency subgroup, and then there was some academic work done by Mark Batty and others that took the draft of the standard, formalized it in mathematics, and realized that there were problems in the formalization in the statements of the standard. So there were fixes this went over there was some looping here, and all this ended it with a C, C++ 11 standard. So I will use the terms C11, C++ 11 as interchangeably, because if the concurrency standard was done as part of the C++ standardization effort, the C committee took the C11 memory model, the C++ memory model, just to ensure compatibility. Okay, so from the 80s to 2011, why did it take so long to get the formal specification? Why is it so hard? And well, it is an old problem. So imagine you take a very simple and innocuous optimization like constant propagation, okay? So you have some source code which you have x equal 14, y is an expression that uses 6, and then the compiler will align the value of x into the value of x in the expression of y, so you get this, and actually any compiler will generate y equals 0 immediately without reloading x. So this looks simple, innocuous, but as soon as you are in a concurrent context, sheer memory, imagine that you start from x and y which are 0, and you do x equal 1, and consider this code. You have two threads. One does x equal 1, and it says if y is 1, then print x. And the other thread says if x is 1, then x is 0 and y is 1. Bit of thinking. Can this program print anything? The answer is yes. So to print something, y must be 1. Y is updated here, and it is only updated if x is 1, which is updated here. So we can imagine this schedule in which x is equal 1. Yes, x is 1, so x is 0, y is 1. Yes, y is 1, print x, and this will print 0. So we expect this program to always print 0. However, this looks a lovely candidate for constant propagation. And if we implement this, then we end up with some code that will always print 1 rather than 0. So you have the compiler that introduces behind your back some new behaviors and probably break your program. So what I plan to talk about in this talk. So we have seen that concurrency and optimization, well, it is not so simple. And there will be a first part in which I will recall what the C11 standard says. So there is a part for the layman, and there are also escape lanes for the expert programmer. Then I show you some applications, some things that we can do once we have a specified model, concurrency model. And in particular, I will present a project on compiler testing via theory of sound optimization in C11. And at last, I will show that, well, the escape lanes are not the ultimate solution. They can be seen as, they're a bit of a Pandora's box. And I try to hint.
Sorry, one quick question. Wouldn't those two issues be fixed if we use just atomic variables there?
Or can you ask it in half an hour?
Okay.
And then I hint the way forward. So, the layman solution, let's forbid data races. Well, you know all this probably. We say that two memory accesses conflict if they access the same memory location, like a variable, and at least one access is a store. And we say that a program has a data race if two data accesses conflict and can occur simultaneously in what is called a sequentially consistent execution, which is essentially an interleaving of the memory accesses. And then we say that a program is data race free on a particular input if no sequential consistent execution, so no interleaving of the memory access, results in a data race. Now, nothing of this is new. Okay? ADA 83 already had this definition, and in particular, if you have an ADA program with a data race, then, well, it is undefined, it is unknown. And the POSIX thread specification said the same. Data races were errors. And this is also what C11 does. So data races are errors. However, C11 is used to write a lot of low-level system code. And this code is intrinsically racy. So you cannot live in a data race-free programming language that gives no semantic to racy programs. And to allow programmers to write low-level system code using C11, the C11 memory model gives expert programmers some escape lanes which are called low-level atomics. So what are the low-level atomics? Well, you get a declaration of atomic variables. So you can, this is C++, but you have the same in C. So you can declare some variables as atomic. Then you get a new syntax for memory accesses, like the name of the variable, the store, the value you want to store, and then you get all these weird keywords which are called qualifiers, like memory order relax, memory order acquire, that specify the semantics that the compiler must ensure for these accesses. Let's look at the qualifiers. So there are essentially four. In the coming four strengths, there is the easiest and the strongest, which is sequentially consistent, which will guarantee, which will impose to the compiler to give you just sequentially consistent memory accesses. There are release acquire, which will give you an efficient implementation of message passing. And then there is release consume, which will give you an efficient implementation of message passing on some architectures, in particular ARM and Power. And then there is a more relaxed that says, okay, no synchronization, I know what I'm doing, give me just a direct access to the hardware memory instructions. Okay, now let's try to understand a bit more what all this means. So sequentially consistent are a bit boring, you will just get the interleavings, but let's try to understand release and acquire. So let's try to implement message passing. Okay? Imagine that Y is a message that the thread 1 wants to pass to thread 2, and so X and Y are 0 in the beginning, and you start by updating the message, and then updating X, which acts as a flag, saying, okay, I finished updating the message. And you have the other thread which is doing, which checks, has the flag been set? If it has been, then I can safely access the message. How does it work? So if we declare the store to the flag as release and the store and the load of the flag as acquire, then the standard says that between the two accesses, you get a synchronized with relation. So whenever you have a load, an acquire load that reads a value written by a release store, you get a synchronized with relation between the two events. Then you get the program order, which is called sequence before, and then the C standard says that you have to build a relation which is between events, which is called happens before, which is the transitive closure of sequence before union synchronized with. And the standard says that non-atomic loads like this must return the most recent write in the happens before order. Okay? And in this case, the most recent write in the happens before order is the update of the message. So we are guaranteed that message passing will work. What if we write the same program with relaxed? Okay? So instead of release acquire, we use relaxed. Well, we get a data race. Why? Because there is no synchronized with relation between these two events. And then we end up with two non-atomic accesses, the two atomic to Y, among which one is a write, and they are not related by happens before. So this program is undefined, can end up with any result. And what if we write everything with relaxed? Well, then we get a program which is well defined, because by definition atomic accesses do not race, but R2 equals 0 is possible. So, which means that here you don't see the update of the message. And this is exactly what the scope of the purpose of relaxed is, that allows the compiler and the hardware to reorder accesses. For instance, here the compiler might reorder these two accesses, so it updates the flag, you see the flag, you don't see the update of the message, and then only later you update the message. Okay? How do we formalize this? How it is specified in the standard? Well, essentially a relaxed load like this one is allowed to see any store, provided that it doesn't happen after it, you cannot read from something in the future, and it's not, so you have to read something in the past, and or unrelated, but it doesn't have to be done by an intervening store, which is HB order between them. So this is a short overview of the C11 model. Now the full model can be formalized in mass and this. And what is great about this is that it enables reasoning about C concurrency, because we know what the semantics of our program must be. So maybe we can go back to our first program, the program that when compiled with GCC 47.02 printed 0 instead of what I expected, which was 42. So let's look again at the program. We had decided that thread 2 is not affected by thread 1 and vice versa. So this program is actually data race free. So the C11 standard states that you can observe only interleavings of this program. And you can build all the interleavings, but they will all print 42. So printing 0 is a compiler bug. Actually, it is a subtle compiler bug. I like to call it a concurrency compiler bug, because it is a miscompilation, but it is a miscompilation that you cannot detect by executing your program in a sequential context, just by running it. You have to put some clever concurrent context to observe the miscompilation. Now, this looks tricky to detect and potentially dangerous. So, can we do compiler testing? What can we try to fix to find a way to test our compiler against these bugs? And, well, the state of the art of compiler testing is a work that you probably maybe heard of, which is called C-Smith, which is a work by Yang, Chen, ID, and Regia, appeared in PLDI 2011. And the idea is simple. You write a clever random generator of well-defined C programs. Okay, and these programs at the end compute a checksum of the memory accesses. And then you compile them with lots of different compilers, okay? As many compilers as you want. And then you execute all the binaries, and you collect all the results, all the checksums, and statistically, if you get one checksum that differs from all the others, then probably your program hits a compiler bug, and well, you start doing test case reduction, and you fill a bug report. And this worked very well, because it reported hundreds of bugs on various versions of GCC, CLang, ICC, and other compilers. But this approach cannot catch concurrency compiler bugs, because here we are generating sequential code, and we have seen that the checksum of sequential code is correct. So can we extend this to concurrency compiler bugs? Well, the big question is, how can we deal with non-determinism? Can we generate non-racy, interesting concurrent programs? Tricky. Can we capture all the behaviors of concurrent programs? Even worse. And what really kills this approach is the fact that a compiler can optimize the way behaviors. So imagine that your program can print 0 or 1. GCC compiles it into a program that always prints 1. CLang compiles it into a program that always prints 0. Both compilers are correct, but you have no way, you don't have an easy way to detect. If you start comparing the results, then you end up with something. I mean, you have no way of detecting if compilation was correct. So, not everything is lost, because C and C++ compiler actually support separate compilation, and C compilers must assume that a function is called in an arbitrary, non-racy, concurrent context. In turn, this implies that C and C++ compilers can only apply transformations which are sound in an arbitrary, non-racy concurrent context. And if by any chance we can characterize which are the optimizations, the transformations which are sound with respect to an arbitrary non-racy concurrent context, then we can reduce the hard problem of hunting concurrency compiler bugs to search for transformation of sequential code which are not sound in an arbitrary concurrent context. And this suggests this strategy. You still have your evil random generator, you have it generates a sequential program, then you take a reference semantics and you get a reference memory trace with all the memory accesses performed by the program. And then you compile your sequential program with an optimizing compiler under test. You get the executable, you do tracing to get a trace of memory accesses, and then you get a final memory trace, and then you compare the memory trace generated by the compiled program with the reference memory trace, and you check if these two, if you can obtain this one from this one by applying only transformations which are sound in any concurrent non-racy context. Now, the idea is simple. Can you make it work? So, step one, you have to decide which are the optimization which are sound in the C11 memory model. So, what is an optimization? So, for the compiler writer, an optimization is probably a sophisticated program analysis that involves some fancy algorithm which is carried over the source code or an intermediate representation, and in general are operation on the abstract syntax tree. So for instance, here we have a loop, okay, at every iteration of the loop, here we access y, and we compute y plus 1, and loop invariant code motion will do some analysis, and then we decide that it can hoist y plus 1 out of the loop. Now, for the semanticist, then we can reason, not in terms of this, because this is too hard, there are too many. On GCC there are 180 passes. I mean, we have no chance of studying if all of them are correct. The semanticist might think in terms of, okay, elimination of runtime events, reordering of runtime events, introduction of runtime events. So this is the trace of this program before loop invariant code motion, and you can see that you have two loads of y, and when you perform loop invariant code motion, you observe that the load of y has been reordered at the beginning, and one other load has been eliminated. So, question. Let's consider a very simple case. So, we write 1 into G, and later in the program we write 2 into G. Under which conditions it is correct to eliminate the first store? Well, of course, there must not be intervening stores or reads to the same location. But what about concurrency? Now, by this definition, a same thread release acquire pair is a pair of a release action followed by an acquire action in program order. And a release is whatever which is a possible source of a synchronization, and an acquire is a possible target of a synchronization. And there is a simple soundness criterion for optimizations, which is, okay, it is correct to eliminate the first one if there are no accesses to G, and there are no same thread release acquire pair in between the two accesses. Okay, why this condition? Let's see on one example. So here we have G, which is 0. We have two atomic variables, F1 and F2. And then we do G equal 1. We do a store of 1 with release semantics. We do a load of F2 with acquire semantics. And then we do G equal 2. Now, this looks like a candidate overwritten right, but there is a release acquire pair in between. What can happen? Well, imagine this context. Imagine that you have a context that waits for this store to be performed, then prints the value of G, which will be this one, and then you store the release, you store 1 into F2, which will unlock this while loop and get this to update. So here we have 2 synchronization. Thread 2 is not racy because of these 2 synchronized with relation. And this guarantees that this print can only read 1. However, if we perform overwritten write elimination here, then you get this print that will print the initialization value, and so you will get a new behavior, and this is bad, and this is not correct. Now, imagine that we have just one release. Why it is important to have a release and acquire in program order? Well, because if you have only a release, this context is racy, because you have no synchronization between these two. And you can go on, and you can characterize all the correct elimination of memory accesses. Okay? And here there are some, so like write after write, read after read, read after write, write after read, and so on. Okay? And we can prove all this correct in mathematics against the C11 model. And we can also have correctness statements for reorderings, merging, and introduction of events, which are other things that compilers love to do. So now we have our theory. Can we make this into a tool? The answer is, well, let's see. For the random generator, we take sysmis and we extend it with locks and atomic accesses. This is easy. To get the memory trace, we perform binary instrumentation using PIN. For the reference semantics, well, we don't have a reference semantics for C, unfortunately, not yet at last. And so what we can do is compile it, cross our fingers, compile it O0 with GCC and CLAN, and then again get a trace by binary instrumentation. And then we wrote a tool that can analyze the traces to detect eliminable actions and match the two traces. Can we see it in action? Let's see. So this is a randomly generated, well-defined program. Okay, and we start tracing it. So there is some initialization. And then there is the reference semantic that says this is a sequence of memory operations. Well, if we compile it with GCC O2, then we get this sequence of memory operations. And so we start analyzing this one. Can we obtain this from this by only sound elimination and reordering and introduction? And the answer is, well, we start analyzing this. We detect which are all the eliminable accesses. And then we realize that, yes, if we eliminate this 4 here, and we reorder these 2 and these 2, then we get this trace. And in this case, well, since we can match, the program has been compiled correctly. However, if we take our initial miscompiled example, we'll see that the reference semantic says that this program should only load A with 1. And this program, while the GCC02 memory trace loads A, but also loads B and stores B. And you get some memory events that cannot be matched in the reference semantics. So you detect a compiler bug, you perform test case reduction, and you fill a bug report. Okay, which are the applications of all this? Okay, now, all this is good, but not all of C, C++11 is good. Let's look again at the qualifiers. Sequential, consistent, and release acquire are reasonable. Release consume is hard to implement, and as far as I know, it is not implemented by any compiler today. It is treated like release acquire. And more relaxed is definitely too weak. And I'll show you this with one example. This brings us in a world which is called out-of-scenario reads. Small shorthand, all the accesses from now on will be on atomic accesses and will be with relaxed semantics. So, x and y are 0, choose threads. This copies x into y, and this reads y, and updates x with 42. Well, this program can end up with R1 equal R2 equal 42. Why? Because everything is relaxed. The intuition is that the compiler might reorder these accesses, might reorder these 2 accesses. So you get x42. R1 is 42, y is 42, R2 gets 42. Okay, this is what is expected. And now I do something a bit evil. I will replace this write of 42 by a simple copy of y. So here we have x into y, and this time y into x. And now, if we take the semantics of relaxed, let's recall it. The semantic of relaxed says a relaxed access can return any memory write, provided that it doesn't happen after it, and it is not hidden by any writing happens before. Here happens before it's essentially empty. And this means that we can make an execution in which these writes write 42, and the reads are justified by the fact that there are these writes of 42. Let me say again. The memory model is an axiomatic one. What I mean by that is that it says, build all the possible execution by running in an arbitrary context, particularly a context where you write 42, and then filter them according to some rules, like non-atomic reads must only return, can return any relaxed write which is not hidden by happens before. And so this is an allowed execution. But the value 42 was never written by the programmer. Okay, and we say that it appears out of thin air. Can we justify this in terms of compiler optimizations? The answer is, if you are bad guys, yes. Because imagine that the compiler imagines that x is likely to hold 42, then it might do some kind of speculation like, instead of copying x into y, it starts, y is 42, because, let's guess. And then I read x, and if by any chance I was mistaken, let's fix my mistake. And the result of this is that if you execute this with this, then y is 42, 42 out of thin air, and you get, yes, R2 is 42, so you update x. And then later, what you get, you read x, but x is now 42 because it has been updated by this one. Yes, I was right. And you do nothing, and you end up with a 42. Now, the good news is that this doesn't happen in practice. So a big thank you to all the compiler developers and hardware developers in the world. But it is allowed by the standard. So it is failure on the other side.
Okay, I've got another question. Because from what I know, relaxed reads only ever should be used for like implementation of simply linked lists and things like that, in which the relaxed model is actually right, because you cannot cache like reads from memory address you don't have and things like that. So it actually should work there if you don't have like interleaving values of this type, just single sort of writing and reading. Or am I wrong in that?
Okay, I wanted to show some consequences of out of thin air reads, and if you wait a few seconds, I will reinsert 3 slides that I removed that will answer to this exact question. If you can be patient a few seconds. I just have to go down and say, don't skip these slides. Don't skip this either. Yep. What's this? Yeah, this is fine. We can skip that one. So, let's use low-level atomics to implement low-level data structures, like linked list. Okay? This is a very simple linked list. And so here, imagine that your heap looks like this, and then you do this. R1 is saying next, so R1 is this one. And you say R1 next is equal to A, so what you do is actually this. Fine? Now, I do this in parallel, so everything is atomic relaxed. So I do this in parallel on 2 disjoint data structures, A and B. Okay? So imagine that we start from here. thread 1 only operates on A, and thread 2 operates on B. Okay? Now, imagine that the compiler speculates that R1.next here is B. Why not? It might. And imagine that it speculates here that R2.next is A. Then you end up with this one, which is very bad because it breaks all our basic intuitions about memory and sharing. So the semantics of relaxed is very relaxed. You can, of course, implement this with stronger atomics, okay? But it is dangerous to use relaxed. And another dreadful consequence I wanted to show you was a bit more complicated program. Sorry, I have to move this way. I hope you can hear me. So imagine x is equal to y, and A, everything is 0. A is non-atomic, x and y are atomic. And so what does this do? One thread that says A equal 1, and then it says if x is 42, then write 42 into y. And here you say if y is 42, if A is 1, then write 42 into x. Now, let's think a bit about this code. Remark 1, this code is not racing. Because, okay, a bit dangerous, because here there are no synchronizations and, well, we have two non-atomic accesses to the same variable, but there is no consistent execution in which the read of A occurs, because if there was one consistent execution in which this one occurs, then, let's recall the semantics of non-atomic reads, they must return the last write in the append before order. And the last write in the append before order, there are no synchronization between these two threads, so it must be this one. And this one can only return 0. So this must be false, so this will never happen, so this will never return true, so all the rest will never happen. And so the code is not racing. And A equal 1, of course, and x equal y equal 0 is the only possible final state. However, if we perform a very simple program transformation, which is sequentialization, so we have two things in parallel, C and D, and you put a semicolon, you put one after the other, well, this ought to be correct. We all agree. But if you apply it to these two threads, then we get this program. And now what you get now is that this, you get one consistent execution in which this read can return 1. So you can return 1, or you can imagine the write of 42, and you have the relaxed load that can read the write of 42. And so you get A equal 1, x equal y equal 42, which is also possible, which is again a behavior which has been introduced by program transformation and which is what we want to avoid. So the point is that this, if you use relaxed, then you break common source to source, or for instance, LLVM IR to LLVM IR compiler optimization. Like, I mean, this is very simple, but we can do more complicated example with expression linearization, Roche-Motter reorderings. And, well, this means that we cannot use the C11 model to reason about each step of transformation in the compiler. So, it's a bit sad, the fact that we still lack a really satisfactory proposal. Okay, C11 was a big step forward, still unsatisfying in some respects. And so what's the way forward? Well, we do believe, well, this is very tentative, but I do believe that what is needed is to understand which are the actual effects of what compilers implement and what programmers rely on. And then we can build on that to avoid this semantics that says, okay, if your program has a database, then it has no semantics, or it can read anything which is written. Because, well, we know all the possible transformations, and we have to abstract from that, and maybe we can define highly non-deterministic, but well-defined semantics, and so some of these problems. But by the way, we can go beyond concurrency. This is not a problem for concurrency. In the C standard, there are lots of problems, of lots of subtle points in which, well, whatever the programmers expect and what the standard says greatly differ. For instance, can you do a pointer comparison or pointer arithmetic between pointers to separately allocated objects? The standard will say no, but both are routinely done with the Linux kernel. Okay? So what is C? And what we need is your answer to this question. Peter Sewell and Kevin, who are over there, you can identify from the t-shirt and from the old scan codes. Made a web survey asking about, to investigate, to have your opinion about what C actually is and what is implemented by LLVM, C-lang, and what is relied upon by system programmers. And the eventual outcome, if you help us, will be a clear description of what we can rely on and what compiler developers can actually do. Thank you very much. Questions?
How much of all of this goes away when the hardware does nothing except sequential consistency?
Good question, but you still have all the 186 compiler passes that change your code. So all of this is still present. Actually, for hardware, we have some reasonably clear formalization of exactly what the hardware will do, and which are reasonably abstract so that they can be given to a program. It is definitely easy for x86 and a bit trickier for Power and ARM and GPUs, but it is doable. However, we don't want to tell to the programmer that the result of his program is whatever execution you can get from the compiler applying in some order lots of compiler optimization. So having just the point when you execute in a high-level program, a program written in a high-level programming language, you get these two steps. The compiler reorders your code and eliminates accesses and do all kind of weird stuff, and the hardware does it as well. So even if you remove the hardware layer, you still have the compiler level.
Yeah, so that's very deliberate, of course, because the difference in performance between compilers which don't make those assumptions and those which do is phenomenal. And if you use atomics everywhere in your program, on x86, for instance, about a 400 cycle delay, which you atomic to use.
Yep.
So we really don't want to do that. And so the standard really is there to help define what it is you can do. And if you make a sequentially consistent single-threaded model, then it should also apply to a multi-thread.
Yeah, I mean, to answer the first question, if you take constant propagation, the constant propagation example that I showed, and you rewrite everything with atomic sequentially consistent, then yeah, the compiler will stop doing constant propagation, and you don't have to worry about that. But if your memory model is sequential consistency, then most of compiler optimization become unsound. So for instance, you can eliminate only adjacent accesses. As soon as you have an interleaved access in between, then you cannot eliminate it anymore. And that's a price too high to ask compiler developers to refrain from doing that. And programmers to benefit from 40 years of research on compiler optimizations.
Can you go on to one of your slides about when you applied the sequential consistent on the first program that was problematic, they were trying to remove the B's axis. Can you go back to the slide?
More.
More.
Or is this?
More. No.
Yeah, okay.
Yeah. Okay, no, yeah. Go to the end when it says that the access to G. No, it's not this one. It's the A and B example.
Let's find it.
Just keep going back.
This one.
Yeah. A bit back. One back. No.
Okay.
No, too much.
No, it
No, it was
want
that
this
slide.
one.
It was that slide, but it was a different. No, it was that. You were.
You want this one?
No. The one that
This
Sorry,
one?
Yeah, but you see that you say with the sequentially consistent that you can remove the B. Later on, you had the two B's in the, down here. I don't remember where. But you can only infer about the B here because you know that another thread is changing B. But if you had a third shared memory variable there, C, right, then no other thread changes, or at least not in this context. Then you can't reason about every shared variable in thread 1 that is not being changed but it's in the code. You're only reasoning about B, so the GCC is only doing anything to B there because maybe it knows the thread
Okay.
changes.
No, okay. So this is a magic of data is freedom. Okay. So all these accesses are non-atomic. Okay. And the magic of data is free programs like this one is that the compiler can perform any sequential optimization it wants, provided that it is correct in the sequential setting, without changing the behavior of the program, because only racy programs can tell the difference. So whenever the so having one source thread wouldn't change anything to the analysis that the compiler does here or here. Okay? And when we get 0 instead of 42 here, is really a compiler bug.
No, but when you add the sequentially consistent to A or B now, I don't remember.
I believe.
I had to see the slide. Sorry, I did not want to ask you at the time you're talking to not interrupt you, but now I just never mind.
So I think if anyone's writing this code, the very least they do is make those variables volatile.
Never use volatile for synchronization or
Yeah.
for concurrency.
Yes.
Volatile doesn't tell you anything about
Yes, absolutely, yes. I
about
agree.
data races. So if you have concurrent accesses to a volatile variable, so program is racy.
But it does make the single thread optimization sequentially consistent within the one thread. So if you didn't want a particular order of your the loads and stores, then you can force that.
Don't do that.
But then the hardware won't obey that anyway. The hardware will go away and just do its own thing anyway. So if you do need synchronization of any kind, you need either atomics or data memory barriers.
You haven't said anything about volatile.
Yeah, it's not part of. So what is volatile? Very good question. I should be added to the survey. So volatiles are not really. I believe are not really part
It's
of.
like it's not regular memory.
Yeah, volatile. Okay, so my take on volatile. Volatile should only be used to when you do DMA accesses with some device driver. Volatile tells the compiler to not try to optimize memory accesses to this location. So if you have several memory accesses to a volatile location, those will be performed in order. Okay, but it says nothing about reordering other accesses with your volatiles. Okay, I can show you an example where a compiler reorders something with a volatile, and if you use volatile for synchronization, well, the compiler was allowed to reorder something which wasn't volatile with a volatile access.
Right, so you need to put in an explicit end phase as well.
Yes, why not use atomics?
Then use atomics.
Right, but we didn't have atomics.
Oh, absolutely. But the way forward is to use atomics.